All right, we're well 3 minutes in, almost 4, so I think it's a good time to kick it off. Welcome everyone to another cFLOW webinar. My name is Ivan Lazar Bundalo and I'm a senior R&D engineer at CSEM. And today it's my pleasure to be your host of yet another cFLOW webinar. So this is the second webinar that we are having in the series. There have been some changes to this webinar, but we're going to come to that due to the sickness of one of the speakers. We're going to have only one speaker, but we will have the second talk in 4 weeks' time. So we're going to still have everything that we prepared. Everything will be available to you. So I hope that everyone can see my screen. It probably makes sense to start with cFLOW again, like the last time. So cFLOW is a EU Horizon 2020 project, which stands for coherent ultra-fast long-wave infrared communications. As a part of this project, we are making this series of webinars to highlight different technologies that we have available and the potential use for them and where we are going with these webinars. So what does that actually stand for? That's a mouthful again. So maybe it makes sense to look at the spectrum of absorption of our Earth's atmosphere. So on the right-hand side, we have the old spectrum. So let's say not the old spectrum, but the spectrum that has been traditionally used for the radio, television, and mobile networks. So at the further part of the spectrum, there's very low absorption. This is also where the first satellite and free space communication links were made. Then if we look at the other side of the spectrum, we have the visible spectrum, which is also almost not attenuated at all. That is not really used as much for the telecommunication, but the spectrum which is just outside, which is around 1.5 microns, is the standard telecom wavelength. So that's where we have the fiber optic technologies which were driving the development of lasers, detectors, modulators, and basically the whole system infrastructure that we are having today for the standard communication. And then if we are looking again, so this is the absorption. These are all based on the lower absorption parts of the spectra. If we look over here a bit further down the road to the spectrum where there's from 8 micron to 12 to 14 micron, basically, we have what is called the long wave infrared region. It's also one of the regions with lower absorption in the spectrum, but so far it has been untapped because it was basically prohibited by the lack of technology. That has changed recently with the development of quantum cascade technologies. And this is where this project, cFLOW project, is focusing, developing all the systems and technologies for making use of this part of the spectra for the free space communication. So the goals of the projects are to develop this 8 to 14 micrometer spectrum, to use it for the free space communication and to develop it for the unmatched speeds in comparison to the other parts of the spectrum, so speeds from 20 to 100 gigabits per second. One other advantage is that these devices can operate at the room temperature, so they don't need to be cryogenically cooled, and they're going to be inherently compact systems because they're also making use of photonic integrated circuits, or so-called PICs. So today in our second webinar, as I said, the second part, Borislav is sick, so he will not be able to participate, but we have Salvatore present. So Salvatore, are you with us? I think that you have to unmute yourself.
Sorry, can you hear me now?
Yeah, I can hear you loud and clear. Very good. Thank you for being with us. So maybe just a few words on Salvatore before he starts his speech on the free space optical communication in long wave infrared window. So Salvatore obtained his PhD in photonics and optoelectronics from the Institut National des Sciences Appliquées de Rennes and the University of Rennes 1, so in France, for the development of quantum nanostructure-based VCSELs on indium phosphide for coherent communications and microwave photonics. He then spent 3 years as a postdoctoral fellow at the Laboratory of Infrared Imagery of Cialetti in Grenoble, also in France, working on development and characterization of high bandwidth infrared single photon detectors based on MCT avalanche photodiodes. So all of that for free space optical communication, quantum optics, and astronomy. And since 2021, he has joined 3.5 Lab in Palaiseau, France again. I'm probably pronouncing all these French words a bit wrong, so my apologies for that again, where he joined as a research engineer. So his current activities include the development of 3.5 semiconductor devices for high-speed free space optical communication in mid-infrared window. Once again, thank you, Salvatore, and the floor is yours.
So thank you, Lazar, for the kind introduction. And I will share my screen now.
Just one more thing for everyone. Please send the potential questions to me directly, so I can ask them at the end of the session, so we don't disturb Salvatore while he's speaking. Thank you for that.
Okay, so can you see the screen?
We can see the screen.
Okay. So yes, thank you very much again, and just let's start with this webinar. It is about optical communication in the long wave infrared window. So this is the outline of the webinar. So just a few word introduction, the context, why we are doing that. What is a free space optical link, and which are the competing technologies currently that are developed for addressing the free space optical, let's say, the free space links. The effect of atmosphere on the free space optical transmission, and then a few words on the cFLOW project, so the developing of building blocks for the free space optical in the long wave infrared window. So the why optical communication? The answer is simple, because of the data traffic growth, and that we are we see in this graph that is growing and growing. So we need more data bandwidth, and so that's why we will use optical communication, because they have several advantages. So increasing data rates, also the optical communication are also higher security in data transfer if compared with other technologies. They are immune to electromagnetic interference, and also the optical communication are higher they have higher efficiency and low power consumption, and also small footprint, so the portability of the system is increased, and also the costs are decreased. So we can see here in this slide that there are 4 main criteria to benchmark optical communication links, that are capacity, so how much data we can transfer and how fast, the reach, so how long we can transfer data, and at what cost. These are standard in fiber telecommunication links, but if we discuss about optical communication, there are also another criteria, that is the link availability or stability of the media. As I said, is specific to free space comm. So for instance, in the case of indoor communication, like LWIR or data center, we have a low cost and reach, low capacity in the case of domestic links, or high speed for the data center. And the link availability is not an issue, because typically they are on fiber networks. We have also the last mile problem, that is how to get the data up to the end user. So it's the last mile, in fact, in which we have intermediate cost and reach issue. the capacity must be high, and also we have high requirement on availability. And then there is the most challenging scenario that are airborne and space, in which we have high capacity need, reach, and cost, and the requirement on link availability is also the highest, because we transfer data through the atmosphere. So what is an optical link? We can see here in the image is basically is composed by a transmitter and a receiver. In this case, a bidirectional free space optic link. It can range from some hundred of meters in the case of metropolitan link, up to some 10 of thousand kilometers, for instance, in the case of ground to geostationary satellite orbit. And so we have for the transmitter or even the receiver, we have a telescope that basically is his job is like the array antenna of RF link, and a transceiver or a receiver. So transceiver is imprinting the bits on the optical carrier, and on the receiver side, we are just reading them. So, but in fact, in the reality, this free space optical link is not in vacuum, but is the data are transferred across the atmosphere, so we have losses. And one way to benchmark the free space optic link performance is to realize what we call link budget analysis that consider the output power, the gain of the transmitter and the receiver telescope, and the losses through the atmospheric channel. This will be compared with the receiver threshold, that is in fact the minimal signal to noise ratio to detect the target bit error rate that we want to achieve. And this gives the link margin, the link margin that is one of the criteria to assess performance of the optical link, together with the achievable data rate that is given in gigabit per second, and as I said, the link availability, that is the fraction of time that we have the signal, the signal. So in this framework, we have different competing technologies. So if we have a look on the transmission of the atmosphere spectra, we have on the right side we have the millimeter and terahertz technology that is the main player nowadays. Is because it's a long-last established technology, is permit to get to obtain long reach, but there are some drawbacks of this technology, because it's highly impacted by the attenuation of the atmosphere, in particular by the rain. We are reaching, in fact, the saturation in the product gain per bandwidth. So there is a marginal increase in data rates. Also, we have low directionality links, or it's energy. It's not energy efficient. And it also vulnerable on electromagnetic interference. And also one of the main problem is that the bandwidth is regulated, so it's not free bandwidth allocation. And this technology permit to cover this data rate range from 10 up to 100 gigabit per second. It is it's the one that has been chosen, for instance, in the Starlink constellation by SpaceX. Then on the left side of the spectrum, we have another transmission window that is the shortwave infrared window that is related to all the application developed for the telecoms at 1.55 micrometer. Again, it's a well-established technology that has been pushed by the development of optical fibers and ADFA amplifiers. It permits to get the longest reach with the low latency, and it's also bidirectional, so is energy efficient. It's immune to electromagnetic interference because it's based on the optical transmission. And also the bandwidth is not regulated because it's optical. But again, it's quite sensitive to atmospheric perturbation. Concerning the data rates, we have systems that are working nowadays at 10 gigabit per second, even if we have a demonstration at the research level of 1 terabyte, and the 100 terabytes landscape it can be achievable with this technology. An example is the Mynaric constellation project. In fact, that is using this technology. And then we have the RF photonics that is, in fact, is mixing the two worlds. So we have the best of the two worlds. How to get high capacity at low cost, but the problem of this technology is it has a limited power. So the link distance is less than 1 kilometer typically. The data rates are quite interesting, from 10 to 100 gigabits per second. And then if we look closer, we have also other windows, the transmission windows, that is the sketch here, in which we have the quantum cascade technology that is addressing the LWIR, LWIR window. So in fact, the interesting things of this technology is that it could be competitive in all for all the criteria that I presented before. So in capacity, cost, reach, availability, it also permits high bandwidth. And the interesting thing is that is compared, for instance, with the RF or the telecom technology, is less sensitive to the presence of atmosphere. But the problem is that we have a very low TRL, so very low maturity of device. For the data rates, we start having interesting results because data rates between 1 and up to 11 gigabit per second have been demonstrated in a research lab. So you have here some demonstration, recent demonstration from KTH and École Nationale Supérieure, obtaining the framework of the cFLOW. And so for this, for those that have didn't attend the webinar, I invite you to repair the webinar of NS and KTH. As I said before, communication established in the LWIR, the mid-infrared domain are interesting because they suffer less of the atmospheric effect. What are these effects? Basically, they are related to two things. So aerosol and droplets presence in the atmosphere. This result in scattering and diffusion phenomena. In the case of in longer wavelengths, so in the LWIR, in fact, we benefit from the fact that the longer wavelength is bigger than the typical size of droplets, for instance, and on the fact that also around 10-11 micrometer, we have a dip in the refractive index of the a change in the refractive index of the water that that is resulting benefit to work on at this specific wavelength. So this result also in the mitigation of aerosol attenuation by roughly a factor or even more, a factor of 2 in the LWIR. Then the other atmospheric effects are related to turbulences, so the change in refractive index of the atmosphere. In particular, we have so here in the image we see the beam broadening, so the broadening of the beam that is related to so it's scale with the wavelength, and in this form the beam wandering, that is in fact the deviation of the centroid of the beam. In reality, we don't really have we don't benefit in this case to switch toward the lower the longer wavelength, sorry. And also we have scintillation, that is intensity variation, and again we have a benefit to work at longer wavelength. So all this effect also of course have an impact on the quality of the beam. For instance, here we have an example of a transmission across 10 kilometers on the atmosphere at 1.55. I can okay, it's a video but it's not working.
Salvatore, if you change from the laser pointer, then you should be able to start.
Okay. Okay. So we see that it's ugly impact by the presence of the atmosphere. So if you want more detail, I invite you on the FOE webinar that will be done in a few weeks about the modeling of the atmosphere effect and simulation of the transmission in the long wavelength infrared window. So these are all the effects that I talked about are effects that there are a lot of bibliography on that, but there are also some experiments in real scenario. So for instance, these are two examples. The first one is related to the analysis of the signal strength versus time during the lifting of the fog. So we see that in case of the mid-infrared link, we had the signal that recover faster than the case of near infrared. And also something quite interesting in the second example is that, so this is a comparison in case of different wavelength, the two around the telecom wavelength, at telecom wavelength, and the third one in blue, it's in the LWIR at 8 micron. And we see that in fact we have a visibility, so a decrease in the signal strength that is lower in the case of the LWIR signal during an ASF fog in the present of haze and fog, and even it increases after a raindrop event because the rain washed out some of the particles. So there is a really these are so I see are few experiments in real scenario that are promising for the next development of and the exploitation of this window. As I said, the problem of mid-infrared photonics is that we're compared with other technologies, not mature, except for instance, for the development of QCL, that is nowadays we can find commercially available products, but most of the other building blocks are not available or are available at a research level. So the objective of the cFLOW project is to address this problem. So the main motivation, in fact, was to increase the maturity of the existing building block and also to develop new building blocks to address the LWIR domain, in particular at around 9 micrometer, and to establish a photonic integrated platform in this window. And the objective of the project are in fact to realize an emitter and receiver peak that you are here in the image. The peak are based on the building blocks that are sketched here. So for the peak emitter, we have a quantum cascade laser, modulator, and SOI integrating in the same platform with couplers. And for the receiver photonic integrated circuit, we are developing a coherent, so an heterodyne detection platform that is composed by SOI amplifier and QCL local oscillator. The signal, so the received signal that is amplified by SOA is mixed with the signal of the QCL in a photomixer, so QCD, by using a plasmonic waveguide or the electric MME and beam combiners. So the objectives are to demonstrate free space optical link established at 9 micron with a data rate around 40 gigabit per second, and also working at room temperature. So if we look back to the previous slide that I show you about the building blocks for the mid-infrared, we see that in the framework of the cFLOW project, we are addressing the development of most of this building block to achieve, so to help this technology to mature. So in summary, if I wrap up what I said up to now, the free space comms, it's a rapidly evolving field. We see that there are different competing technology that are pushing the development of free space comms. One of the main difficulties is for FSO link is represented by the effect of the atmosphere, in particular on the losses, and to address this particular project, there are the FSO communication established in the infrared window, in particular in the LWIR window, that can be enabled by the quantum cascade technology. So these are two interesting candidates because as I said, we can mitigate the atmospheric effects on the link, and this is translated with less requirements on optical system. For instance, we can ease up the requirement on adaptive optics or alignment system for this in the case we use this technology. So the direct impact is in the improvement on link availability and even on costs of the system. But as I said, we need telecom grade mid-infrared components. So that's why in the cFLOW project we are pushing the development of these building blocks. So if you want more information about what I said in this webinar, there are some reference that you can have a look. In particular, the first one from Alexandre Delga and Luc Levandier, on which this webinar was deeply inspired, but also the other reference that I cited during the webinar. And of course, you can have a look on the cFLOW project, in which we summarize some more detail of the project. So this is the last slide. I thank you for your attention, and thank you.
Thank you, Salvatore. That was, I don't think that I'm exaggerating. That was truly interesting for me. We already have a few questions. I would also encourage participants, if you have questions, please write them in the chat box. So the first question here is that on a slide 12, why don't the graphs for 1.5 and 1.3 micron go up when the rain stops?
Yes, in fact, the reason is that you have an effect that is by the rain that is washing the bigger particles that are particles that have dimension that are comparable with the 8 micron wavelength. So when they are washed out, they do not contribute on diffraction. So you have an improvement on the 8 micrometer link. You don't see that because these wavelengths are scattered and diffracted by the smaller particles that are not washed out by the rain. So we don't have the same effect on the smaller wavelength. That's why we see it is quite interesting because rain seems to have a benefit, a good impact on the longer wavelength. It's counterintuitive, but it seems to be the case.
Thank you. We have another question which is related to this, but I think it goes to one of the earlier slides. So it says in short wavelength infrared region, it seems to have parts which are in completely transparent part of the atmospheric window. Do they also experience atmospheric turbulence?
Sorry, in which slide?
I think that it's LWIR, so short wavelength infrared window. I think it was, yeah. So this slide is probably good. I think that on the left-hand side, telecoms, what it says, there are parts where the attenuation is low, apparently. So do they also experience atmospheric turbulence?
In this part of the spectrum, you mean?
So I think that at 1.55, for example, there's also.
Yeah. In fact, if I come back on this slide, let's say the atmospheric turbulences are scales with this like this with a wavelength. So there is, for instance, there is a slight improvement if we switch on the longer wavelength for what concern the beam broadening, in even a more impact for what concerns scintillation for the longer wavelength. We don't see really an effect in beam wandering because the deviation of the beam is insensitive roughly at the first order on the wavelength. And also what I show you is that in fact we have also an effect on aerosol and droplets. So longer wavelengths are less impacted by the presence of fog, for instance, or cloud and rain, as I show you. So there are multiple effects that sum up, and at the end, the longer wavelengths are less impacted by the atmosphere.
Very good, thank you. There's another question. Is it possible that telecom-based technology will be replaced by mid-infrared technology in the long term?
So this is quite, I think it's a more philosophical question, because in fact, this is my point of view. We are going to a situation in which probably we will have different technology that are coexisting together to how to say permit that redundancy of the system, because in fact 1.55 can outperform like the LWIR based FSO in other scenarios, like for instance satellite to satellite communication, in which you don't have atmosphere in between the terminals, so you don't benefit in using QC technology. In fact, I have a slide that I can show you, that is this one. This slide shows a scenario in which free space com are in which technology are coexisting. So you have a millimeter wavelength technology for a short range communication. The mirror wavelength that is used for intermediate distances, and then the longer distances, for instance, and telecom wavelength or scenarios in which we don't have atmosphere. And of course, it is a matter of also market, because it's the market that is leading also the technology. So of course, it's not an easy answer, but in my opinion, we are going towards the coexistence of different technology together.
Very good, thank you, Salvatore. There's also one last question. So since we did not have a second speaker, I will still go for it. It's
Okay.
also related with this. Could quantum cascade technology directly benefit from technological achievements developed for other technologies? So, for example, 1.55 micron.
Yeah, I can. I think yes, because in fact there are some. Okay, if you have a look on this slide, of course, for instance, the fact that we are using PIC, so photonic integrated circuit technology that has been developed, for instance, the case of silicon photonic or indium phosphide, so telecom based photonics. Of course, we are reusing some concepts that are being developed for other technologies. We are using in the case of and adapting, of course, but we are using them in the case of quantum cascade technology. I can also think about all the modulation formats that are, let's say, that are so the technology is transparent on that. So we don't need to reinvent everything. I think that point is that we need to increase the maturity of the building blocks that are existing in this wavelength range, and also develop some new building blocks that are currently. For instance, one of the most let's say less mature building blocks is the modulator. So we are here at 3.5 Lab and also École Nationale Supérieure. We are working on the modulators, and these are this is one of the most the less mature building blocks that we need for telecoms.
Very good. Thank you very much, Salvatore.
Thank you to you and to all the person that followed the webinar.
Same. So I would just like to conclude with just a bit more information here. I hope you can see my screen also. So as Salvatore already said, we have our cFLOW webpage where also you will find links for some of the webinars that we are recording. So some of them for confidentiality reasons will not be recorded, but majority will. So please do check over there in a few days' time, and you will find also this presentation. So there's also our YouTube channel that you will find over there. So for the next time, we're gonna meet in 2 weeks' time, where we're gonna have Ronnie, Jose James talking about the packaging of miniature optical components. So it's going to be on Wednesday, May 11. And today's talk that couldn't take place by Borislav will be shifted. So in 4 weeks' time to Wednesday, May 25, with together with Gregory Maison. We will have that then. I think that's it for today. So thank you everyone for your time, for participating today, and I wish you the good rest of the day.
Thank you.
And thank you, Salvatore, once again.
Thank you. Bye.
Thank you. Bye.